Let's strip away the math anxiety and dive into the hidden anatomy of straight lines.
How do simple numbers on a tiny grid actually map out the complex geometry of our universe?
Here's the plan. Placing coordinates, calculating gradients, mastering the magic equation, and seeing what happens when lines collide. Every journey starts at the origin. It's that 0, anchor point where our x and y axes collide.
To pinpoint a spot, just remember, walk along the horizontal hallway before climbing up the vertical stairs.
We've connected the dots, but here's the real problem. How do we mathematically measure that exact steepness?
Enter the gradient, your exact measure of slope. It's simply the vertical rise divided by the horizontal run. Just subtract the coordinates of 2 points. This precise formula spits out your constant, unvarying slope.
Quick visual check. Positive gradients climb up a mountain, while negative gradients slide down into a valley.
Okay, so what if we need to know exactly how long this straight line segment actually is?
We borrow from Pythagoras, build a right-angled triangle, and boom, our line becomes the hypotenuse we can measure.
Need the exact middle point? Just calculate the average of your x-coordinates, then average your y-coordinates.
Check out this data pattern. Notice how every single y-coordinate is exactly double its x-coordinate? That hidden pattern is a line's algebraic DNA, known as the general equation of a straight line. Breaking down the blueprint, m is our constant gradient, and c is where it crosses the y-axis. Build it yourself. Find the gradient, sub in a known coordinate to find c, and write the formula. But lines don't exist in isolation, right? How do multiple lines interact on the exact same grid? Parallel lines share the exact same gradient. Perpendicular lines, though, crash at perfect 90-degree angles.
For perpendicular lines, gradients are negative reciprocals. So if one slope is 2, the other's negative 1/2.
Multiply those two perpendicular gradients together, and you'll always unlock this magic mathematical constant, -1. Time for our final scenario. What exactly happens mathematically when two entirely different equations cross paths?
That collision point is your graphical solution. It's the one coordinate perfectly satisfying both simultaneous equations.
Here, the point 3, 1 is the ultimate bridge, solving both competing equations flawlessly at the exact same time.
Recap time. Coordinates fix position, gradients measure slope, y equals mx plus c is your blueprint, and intersections solve. Next time you spot a straight line, will you just see a shape or an equation waiting to be solved?